So let's start the second lecture on this series on deformation, algebraic deformations. Yeah, thanks, Professor Makhlouf.
Thank you very much, Thiago. Let me continue. I started yesterday. I'm hearing myself, then maybe I should do something to stop. Do you still hear me?
Yeah, we hear you.
Okay, let's do it like this. Okay, yesterday I introduced a little bit associative algebra and also coalgebra and bialgebra, half algebra, in order to talk about quantum groups, which are a sort of deformation and a good motivation for deformations. And today, let's move to Lie algebra, which is the other main algebraic structure. Let me recall some definition. Lie algebra. In fact, I am interested in non-associative algebra, which includes associative algebra, and they are all given by a vector space. Then here for Lie algebra, usually we use G as a vector space over K. And a multiplication is usually denoted by a bracket like this, going from J, tensor J to J. And it has to satisfy two conditions. The first one is skew symmetry, satisfying first skew symmetry, which means that xy should be equal to minus yx for any xy in J. And the second condition is a so-called Jacobi condition, which is xyz plus zxy plus yzx equals 0. And this is a so-called Jacobi condition. I mean, this structure is very important. It was started in works about differential equations, studying symmetries, and it's related to Lie groups, which plays an important role there. And it's due to Sophus Lie, this Norwegian mathematician. And now it becomes a really very important tool in various domains in mathematics. And now these algebra are connected to associative algebra in the following way. We have this, if you consider an associative algebra, if A dot is an associative algebra, then by considering the commutator, if you set the bracket xy is x dot y minus y dot x, then this A with this bracket is a Lie algebra. Okay, then this is a way to construct a lot of Lie algebra. And for example, if we consider A example, all this or the matrices, I mean, or some type of matrices could provide, which formally as an associative algebra could provide examples of Lie algebra. And if you consider, for example, matrices n matrices over K, then you can construct over this by taking the commutator. This is a non-commutative algebra, of course, and you can construct a bracket in the following way. I mean, by taking the commutator, and if you take elementary matrices, for example, Eij, Epq, which means that you put 1 at position Ij and 0 elsewhere, and then this will become, using this bracket, a Lie algebra. And let me write the formula, it could help. Delta Gp, this is a Kronecker symbol. E Okay, then let me continue with examples of Lie algebra. In fact, I don't know if people are familiar or not with such things. Maybe Princey will say yes. Okay, then here let us denote this by G, L, and K. Then this is the corresponding Lie algebra. Okay, then we have some now we can do the same, as we know that there is a correspondence between matrices and linear maps over a vector space. And now if we consider GLV to be the set of invertible endomorphism over V, and V, then we can again here construct GLV, which is a linear, which also a Lie algebra, and this is a subalgebra, a sub-Lie algebra of GLN, maybe this way. Okay. Okay. And so some particular case, maybe if I take, for example, these matrices, and this is a subalgebra as an associative algebra, and here we can get so-called, then we have 3 generators, which we can denote by X, Y, and Z, and that this will give us, and let us denote by, oops. Okay. X, Y equals Z, and this is a so-called Heisenberg algebra, Lie algebra. Okay, and maybe another interesting example is given by traceless matrices, and let us denote by SLV the set of matrices M in GLV such that trace of M is 0, and this, and also maybe then we can get also in the Lie algebra, and we can also consider SLV given by matrices in GLN K with trace of A is 0. And for example, if we take n equals 2, we get an interesting algebra, and which will play an interesting role later in my lectures. And we can take, this is 3-dimensional algebra, and we can consider as generators H, E being 0, 1, 0, 0, and F being 0, 0, 1, 0. And this is a so-called, this is called SL2, and this is semi or a semi-simple Lie algebra, and the brackets here are given by H, E equals to E, H, F equals minus 2F, and EF, this is H. Huh? Okay, then this is an interesting example. Now we started with associative algebra and got a Lie algebra by taking a commutator. Now we can also address the question about all the multiplications that give by a commutator a Lie algebra. Such algebra is called Lie admissible algebra. And they were introduced and studied by Albert in 1948. And this Lie algebra seems also important. This type of algebra seems also important in physics. And what is a Lie admissible algebra by definition? Then if we consider a that is a Lie admissible algebra if the bracket xy defined by commutator defines a Lie algebra on A. Okay. And of course, we have an example. We have seen an example. All associative algebra are Lie admissible algebra. Associative algebra are Lie admissible. Now we can try to characterize this this type of algebra and also try to classify them somehow and provide also maybe other examples. And one approach consists of considering first the characterization and also subgroups of permutation group. Let us define, okay, then we have some characterization using some trilinear operation. Let us denote by associator a trilinear map defined as x, y, z minus x, y, z, and this is a so-called associator. Of course, if the associator of x, y, z is 0 for any x, y, z, then we have an associative algebra. That's right. Huh? And we can define S, x, y, z to be another trilinear operation using this associator. Then the associator of x, y, z plus associator of y, z, x plus, then we use the cyclic permutation here, z, x, y. Okay. Then then we have this proposition. A non-associative algebra A dot is Lie admissible if and only if S, x, y, z equals S, x, z, y. If you have this S, x is the same if we permute y, y and z. Okay, and this is one characterization. And now we aim to try to provide some other examples. And first we define what we call G associative algebra. Then first we start with G being a subgroup of S3, the permutation group S3. Then we say that a binary algebra or a binary multiplication mu defines a G associative defines a G associative algebra if we have this following condition: if the sum over all the permutation in J minus 1 epsilon, the signature of sigma, the permutation, mu of mu sigma 1, mu, I mean, I can write it using the associator now, why not? I mean, the associator of x sigma 1, x sigma 2, x sigma 3 equals 0. This is what we call a G associative algebra. Then this associator uses, of course, the multiplication mu I was talking about. Okay. Then, of course, one example here. If I consider G defined only by the identity, then G the identity associative algebra, and this is exactly associative algebra. Okay, but of course we may have other examples if we deal with other subgroups of S3. And the interesting result here is that any G associative G associative algebra is Lie admissible. Then the proposition any then of course with G being a G subgroup of S3, then any G associative algebra is admissible. Okay. Then it is clear that if G is given only by the identity, then this is true. One can check it directly. Of course, we can prove this proposition, but I don't have time to do it. We can find it in some papers. And now, but what I want to do here is to show you other examples of G associative algebra. In fact, we know all the subgroups. The subgroups of S3 are well known. The subgroups of S3 are, then let's denote by G1, the one defined by the identity, G2, the one defined by the identity and transposition 1, 2, G3, the one defined by the identity and transposition 2, 3, G4, this is also given by a transposition, and now this is 1, 3. And G5, this is A3, the alternating group. And G6 is S3. Okay, then if we want to express the fact that the multiplication I mentioned here satisfy I mean, if I want to write down the fact that that the multiplication satisfies Jacobi condition, in fact, what we get is this formula with G being S3, S3. Okay. Then can you see my notes or not?
Yes.
Okay. Okay, then maybe what I want to show, for example, G3, and this G3 associative algebra. That is G3 associative algebra. Then they are given by the permutation corresponding to the identity, and the permutation which is transposition 2, 3. And if we want to write this down, then what we get is mu of x mu y z minus mu of x mu zy equals mu of mu x y z minus mu x z y. Okay. In fact, these are called pre-Lie algebra. They are called pre-Lie algebra. Okay. And if you take G2, then you get similar thing. And this is displays only on permutation also between y and z. If you do it for between x and y, then this is given by G2 associative algebra. Are called Wimberg algebra. Okay, they are somehow left pre-Lie algebra. And this pre-Lie algebra, you can also find them under the name right symmetric algebra or right symmetric algebra. Okay. Then we have more than these associative algebra being Lie admissible. And of course, if you take other subgroups, then you get other identities, and these type of algebra are not studied yet, and then we don't know their property. But the only property we know, and we can point out here, is the fact that they are Lie admissible. Okay, but these pre-Lie algebra are pretty interesting and used in several places. Okay. Okay, then this is one way. I mean, what I discussed here is maybe for example, if we come back to associative algebra, that what we mentioned here is if we take the category of associative algebra sorry. Then we have a functor going from this category of associative algebra to the category of Lie algebra. Okay. Then now what we are interested in is to see whether we have a joint functor, and we have a functor going from the category of Lie algebra to the category of associative algebra. Let's call it L, Lie here. And we want to study the functor going from Lie algebra to the category of associative algebra. And this functor we denoted by U, and it gives, it associates to any Lie algebra. If you consider any algebra here, we associate a so-called the enveloping algebra, which is associative. The main difference between these two functors is if we start here with, for example, if we are dealing with associative algebra of finite dimension, then the dimension of this Lie of the Lie algebra here is the same, because we consider the same vector space and the bracket defined here on this vector space. But if you start with the Lie algebra, in order to associate an associative algebra, you need to get something which is in fact infinite dimensional. Okay, then of course what we want to do also is to deal with their representations. What we aim to have is starting from a G representation, how to get a UG representation. Okay, and then let me now explain a little bit how to go from Lie algebra to enveloping algebra. Maybe I need to recall what is a G or a left G representation. G is a Lie algebra now of a K, a commutative ring or a field. Then a G representation of G, of this Lie algebra J, is a K modulo M, it's denoted by M, and a K homomorphism J tensor M to M, such that X, Y, A minus Y, X, A, this is equal to the bracket X, Y, A. Okay, and here X, Y are in J and A in M. M being vector space here. Now we aim to associate to Lie algebra J an associative algebra UJ that this G representation, a J representation of J, may be viewed as UG representation and vice versa. Okay. We aim to construct an associative algebra UJ, we denote it by UJ, such that every J representation may be viewed as a UJ representation. then here, of course, in this second part, I'm dealing with representations of associative algebra, which corresponds to modules somehow. And now how to do that? In fact, how to construct this UG? We use a tensor algebra. Then G now is viewed just as a vector space. Now construction. Then we let Tj to be a tensor. Oops. A tensor algebra of vector space, let's say vector space J or K module J. If we are dealing with the commutative ring, if K is a commutative ring. But of course, if K is a field, then J is just viewed as a vector space. And what is this Tj? And Tj is given by direct sum T0 plus T1 plus etc. Tn. And what T0 is K times 1. Then here T0 is, maybe it's better to put G here as well. Then T0J, oh, sorry. This is K times 1, the unit. And T1J, this is J. And Tnj is J, tensor J, n times. Okay, then here we can, then Tj, then Tj is an associative algebra, and this is given by these sums Tnj, and the multiplication here is the tensor product. I mean, just by concatenation, we get a multiplication here, which is associative, of course, and then this Tj is endowed with an associative algebra structure. And now, how to construct this correspondence with Lie algebra? Of course, this is not using at all for the moment the Lie algebra. In fact, we have to take a quotient of this in order to get our enveloping algebra. We define an ideal I to be the ideal. Sorry. Is the ideal generated by the elements x tensor y minus y tensor x minus bracket xy, where for x and y belonging to J. And Uj, this enveloping algebra, this is exactly Tj quotient by I. And this is the enveloping algebra. This is, of course, an associative algebra. And this is the enveloping algebra of the Lie algebra. And in fact, this construction is universal. And this construction is universal. That's why we call it also universal. We say universal developing algebra. In fact, if you take another algebra satisfying the property I mentioned in the beginning, then in fact, up to homomorphism, it's the same as this UG. That's what it means. And now we have here an algebra which is infinite dimensional, but it has a very nice properties. The first one is when you have an algebra, you are interested to provide a basis, huh? And of course, if you take all the monomials, you get a basis. But it turns out that we have here, if you take ordered monomials, then this is enough to generate the whole algebra, and this is known as the Poincaré-Birkhoff theorem. Poincaré. Theorem. Then if this is a general theorem, if G is a free Lie algebra with K, and if we take a basis of J, let Xi be a basis of J, of the Lie algebra J, and I alpha 1 alpha p be a finite sequence of indices and now we can set we set we can in fact we have what I said before, we have to embed the elements. In fact, what we do is maybe it was not clear, but what we have here, we have J, which is embedded in Tj, and then embedded in UJ. Huh? Okay. Then the elements of J are embedded in Tj by a map I call sigma, and it turns out that the map, sorry, the map sigma is the map going from J to Uj. Like any element here is embedded in Uj. Then I have to, I can denote Y alpha to be sigma or X, yeah, sorry. In fact, when I talk about XA, XI in J, I mean sigma in Uj. When I talk about XI in J, in fact, I mean the sigma of XI, which belongs to this is in Uj. Okay, this is what I mean. Oh, sorry. Okay. Then let me say it simply. 45. So sorry. In fact, I could say that XI1 alpha 1, XIP alpha p, the monomials these monomials define a basis of uj. This is okay, and then this is for of course for ordered sequence for increasing. Then here I1 smaller than I2. It is clear if I take all the monomials. I told you that this defines I don't know if it's a basis, but generators of uj. They generate all uj. The monomials generate all uj. But here I am considering just ordered monomials, and these ordered monomials turns to be generators and also linearly independent, which means that they form a basis for this uj. And this result is very, very important and very useful. Very useful. Huh? Okay. And maybe last observation for this is put me back to what to Hopf algebra. Then here I said, I just mentioned here that this uj is an associative. uj is an associative algebra. And in fact, it carries a structure of Hopf algebra. It carries a structure of Hopf algebra. Then if I want to construct a Hopf algebra, as I mentioned yesterday, I need a co-multiplication. Then the co-multiplication is defined in this way. Then delta of x, then this is 1 tensor x plus x tensor 1 for any x in j. And we have also to define it on the unit. Then delta 1, this is 1 tensor 1. Then this is the co-multiplication. Of course, if I define it like this, you could ask me how to get the co-product or the co-multiplication on x1 times x2 or x1 times x2. Then this is then we get delta of x1 to alpha 1 xn to alpha n using the compatibility condition. Which states that the delta is an algebra map. Okay, then in fact, delta of x1, x2, then this is delta of x1 times delta of x2 in the tensor product. Here I put a dot, bigger dot to mention that here the dot, here the multiplication is in the tensor product. Then it's an algebra map. Then of course using these two definitions, I mean the definition of the coproduct on the elements of J, this is enough to get the coproduct on any elements of Uj. And now what about the co-unit? Then epsilon of x, this is 0, and epsilon of 1 is 1. Okay, then this is the definition. Then this is the co-product. And this is the co-unit. And what we need now is to define the antipode, because using the multiplication and the unit and the co-multiplication and the co-unit, what we get is they call by algebra. Now, in order to get a half algebra, I need to define an antipode, and the antipode S of x1 xn. This is the multiplication, because here, of course, this uj is polynomial somehow. Xn, this is minus 1 to n xn minus 1 x1. Okay, this is the definition of the antipode. Okay, but then any enveloping algebra carries a structure of a Hopf algebra. And what is known, to try to talk a little bit about deformations before defining them properly. If for example, I take SL2, U of SL2 U of SL2, the enveloping algebra of SL2. This is a semi-simple, a semi-simple algebra. Algebra as an associative algebra, which means that we cannot deform it. This is a property I could explain later. We don't have deformation of this. That's why we were interested in constructing quantum groups, which provides the deformation. Then if I want in this minutes left, I could maybe just define define a quantization of this USL2 and quantization of SL2. And then quantization of SL2, which is denoted by UQ SL2. This now to do this, we define it using I mentioned before that this SL2 is three-dimensional. It's defined by E, F, and H. Then the Hopf algebra structure on UQSL2 is defined with 4 generators with variables E, F, K inverse, and the relations K inverse. This is same as K inverse K, and this is 1. K inverse. This is Q square E, and KF K inverse. This is K minus 2F, and the bracket EF. This is K minus K inverse over Q minus Q inverse. And now what about the co-multiplication? Delta E, this is 1 tensor E plus E tensor K,
Excuse
delta
me,
F.
sorry to interrupt.
Yes.
I have not understood what is exactly the quantization of SL2. Could you repeat?
The quantization of SL2, it's a deformation. Even I didn't understand and didn't explain what is a deformation, but it's a
deformation of
it's a deformation of the enveloping algebra.
Ah, okay.
Then we have to deform the multiplication and the co-multiplication.
And Y has 4 variables.
Why? What?
Y has 4 variables.
Because in the enveloping algebra, I have added the unit. I have the four-dimensional algebra, but the unit I can express it just as using the K inverse, and my unit is just the K inverse. In order to handle the unit, it's better here for this the quantization to consider four variables instead of 3 variables. These are the generators somehow.
Okay, thank you.
Then because since I have the variables in J plus the identity or the unit, now we express everything using these 4 variables, and the unit could be deduced from the multiplication of K and K inverse. Is it clear?
And almost. And then all the quantizations of all these deformations of the universal enveloping algebra are also Hopf algebras.
Yes, exactly. Yes.
Okay.
And in fact, what we have here, this is an example of quantum. And this is the first quantum group, and it was constructed by Kulish, one of collaborators of Fadeev. Okay.
Yes.
Now let me complete the definition of this quantum group. Then this is K inverse tensor F plus F tensor 1. Then delta K, this is K tensor K, and delta K inverse, this is K inverse tensor K inverse. Then we say that they are group-like elements, this K and K inverse. And epsilon of F and E, sorry, then epsilon E F, this is 0, epsilon K inverse 1, then they behave like a unit, because for the unit, epsilon 1 is always 1 in a Hopf algebra. Now, what about the antipode? Then S of E, antipode now. SE is minus E, K inverse. SF, this is minus KF. SK, this is K inverse, and SK inverse, this is K. Okay. Yeah. This is the deformation somehow of USL2, of the enveloping algebra of SL2. Of course, I told you that if we consider the multiplication, in fact, we don't have deformation, but if we consider it as a Hopf algebra, we have deformation using this parameter Q. In fact, when Q tends to 1, then what we get is USL2. This is what we mean by deformation. We have a parameter, then you have a family of algebra, which is which are providing a deformation of this USL2. And here you can see the first quantum group. Huh? And then what I didn't say yesterday, why we call them group? Because if you take the dual of Hopf algebra, it is always a Hopf algebra. Huh? Okay. Maybe I should stop. Huh? Is it clear? Do you have any questions or remarks or comments? And tomorrow we talk about formal power series, homology, and maybe star deformations.
Please, Nafet.
Yes, Christina, yeah.
Sorry. How you obtain the relations, multiplication in this case?
So just one moment, because
well, the question is more or less if there is a procedure to deform.
For quantum groups, no. I mean, for quantum groups, there is no procedure to deform. I mean, when I will start this one parameter formal deformation, there I will provide a machinery to deform using parameters and explain how to deform in general and for any algebraic structure. But for these quantum groups, there is no general machinery. I mean, to provide deformations.
Mm-hmm.
I mean, for families, for example, for SLN, you could have you have a machinery, but not for any enveloping algebra. It's not possible. Huh?
Okay.
But for other algebraic structures, of course, we have a machinery, and this is maybe the main things in my lectures, and I will talk about this tomorrow or the day after. Huh?
Mm-hmm.
Okay.
Okay.
Other questions?
Are there any other questions or comments? There's one question here. Oh, sorry. Go ahead.
For the Lie algebra SL2, you said that it doesn't admit deformation. Right. It's true in characteristic 0, but if you are in characteristic 2, it admits deformation.
Oh, maybe I have to ask my friend Sofiane Boarouj or Laites about that. I don't know. Maybe. I'm sure by characteristic 0, we don't have deformation. I will tell you.
For characteristic bigger than 3, for characteristic bigger than 3, we don't have deformation. But in characteristic 2, there is deformation.
And this maybe was provided by Laites and Boarouj and so on, this group, right?
Yes.
Yeah. Okay. Yeah. In fact, here I am just talking about things in characteristic 0. Positive characteristics are more complicated, and there is some. Even I mean this also. Simply algebra or simply algebra and simply algebra and positive characteristics are also different. Huh? There is more. There is Millikian algebra and so on. Huh?
Millikian data. Yes. Yes. Okay. Thank you very much.
You're welcome.
All right. There's one question on the comments. That's if you could provide any reference for further consultation. I believe you did.
I can provide some notes. In fact, I'm finishing a book about deformation. Notes are interesting.
Yeah, that'd be great. If there's no more questions, or go ahead.
There is about quantum groups. You can find some reviews. On archive or on internet. Huh? If you Google quantum group, you could find it easily. So some reviews, but they can provide references also.
Yeah, that'd be great. So let's thank Professor Makhlouf again.
Thank you. It's a pleasure.